For putting together this rather nice and big event and inviting me to speak. So this is a conference on quantum condensed matter, and what I'll try to do is address some questions motivated by condensed matter or quantum statistical mechanics type topics, but we are trying to answer them using some ideas from quantum information theory. And so I should speak there. Okay. All right. So the title of the talk is information phases in scrambling quantum dynamics, and what I'll try to do is give you this idea that if you have dynamical quantum systems which are chaotic or scrambling, then you can sort of characterize their behavior into qualitatively different ways using how quantum information is stored or encoded in those objects. And before I start, I should thank my PhD students, Alan Sherry and Saptarshi Mandal, who sort of did all the work. And all of what I'm going to talk today is sort of in these two works, but these other two works are also mentioned because they were sort of quite instructive in teaching us various things about this problem. All right, so this is a sort of brief outline of the talk. So I'll basically define what are called projected ensembles and deep thermalization. And it would be like a sort of generalization of thermalization that you might have heard about in the last few days, or something that Shubrata this morning gave a very nice introduction to. And from there, I'll talk about deep thermalization of mixed states, and then using this framework, I'll sort of motivate this idea of information phases. Okay, so just to recap, when we talk about thermalization in isolated quantum systems, what we really sort of say is that there is a small subsystem A, and the rest of the system sort of acts like a bath for that subsystem, and sort of effectively thermalizes it. The temperature or whatever quantities you need to describe the thermodynamic ensemble are set by the initial condition and possibly by the sort of unitary operator that affects the time evolution. Now, when you sort of do this, the key point is that any local observable which is supported on this subsystem A is essentially given, or expectation value of that is essentially given by the corresponding value in a thermal ensemble. That's like a one slide introduction to thermalization in closed quantum systems. The key point here is that this reduced density matrix of this subsystem A should also be a thermal density matrix, and that's just because in the previous slide I did not mention which operators in the subsystem A should satisfy thermalization. Now, since all operators in the subsystem A should satisfy thermalization, it stands to reason that the entire density matrix should be given by a thermal density matrix. Now, to get this density matrix, what you are sort of formally doing is you have the state which has been evolved from some initial state, and you are tracing out your bath. Now, when you trace out bath, sort of in plain English, it just means that you throw away all information about the bath, right? Now, this is how thermalization used to be studied and is being studied for various interesting and important fundamental questions. But what you can actually do is you don't throw away the information of the bath. You can do a bit better, which is you can do measurements on the bath, okay? And when you do measurements on the bath, you again do not throw away the measurement outcomes, but rather retain these measurement outcomes, and that sort of gives you a classical register. For example, suppose I have a set of qubits and I do a, say, measurement of the sigma z component of the spin, then I'll get a classical readout like this, 0 is spin up, 1 is spin down, and so on. Now, given this classical output or classical bit string, conditioned on this bit string, there is still a quantum mechanical state in the subsystem A, right? And of course, these measurement outcomes are probabilistic. They satisfy the bond rule probabilities and so on. And what that means is I have the so-called projected ensemble, right? So it's an ensemble over the possible outcomes in the subsystem in the bath B, and then they come with the probability P of ZB, and there is a conditional state on this. Now, once I have this ensemble, it's like a probability distribution, right? I mean, it's an ensemble of states, each of it comes with a certain probability. And the moment you have a probability distribution, of course, you start computing moments of it, right? But this is a probability distribution over states. So how do you actually define an arbitrary kth moment of this ensemble? The way you define this is you take the state, or take any particular state, compute the density matrix corresponding to that pure state, and then sort of take a tensor product of it k times. And then you add them up over all the possible states that you have in the ensemble with the respective probabilities. Yes.
Just a question. Like, since you're getting probability of safety, is it measured over several intervals several times?
No, there is one state. There's a single state. You can measure it several times, and every time you will get a different outcome, right? So it's like, you run this experiment many times, okay? But of course, this part is deterministic, so you sort of get the same state before you do the measurement, okay? All right, so now one thing that's important to notice here is that this kth moment of the projected ensemble actually is again a density matrix. It's again a density operator, which lives on a larger Hilbert space. It lives on a Hilbert space which contains k replicas of your original Hilbert space. That's what, mathematically also the tensor product means. Now, first of all, at this stage it might seem like, this is just some generalization of thermalization that I'm doing because I can. And, why am I at all doing this? So let me say a bit about this. But before I say that, just notice one thing, that if I put k equal to 1, that's literally the original reduced density matrix that you had without invoking measurements. The measurement just happens to be, yeah, Arti.
So I'm a bit confused because measurement will reduce your entanglement, right?
Yes, between A and B. I will come to that. Just hold on to that question for a minute, because see, when you trace out, what you're doing is you're still interested in the subsystem, right? So at the end of the day, what you're interested in is the reduced density matrix of your subsystem A for thermalization purposes. And that reduced density matrix is just getting, given by tracing out B. What I'm now saying is, if I, you can equivalently think of the trace as doing a measurement on B and then summing over all the outcomes of the effective k equal to 1 limit of this problem, right? So that's why, in that sense, when you trace out B, you have already killed the sort of correlation between A and B. So in that sense, yes, but the point is that now instead of having just the reduced density matrix, I have higher moments of this ensemble. The reduced density matrix is just the first moment of this ensemble. So I have higher moments of this ensemble, and they actually contain information that you cannot reconstruct from the density matrix, right? So that automatically tells you that you actually have a lot more information than what you would have had just with the density matrix. Right, so now how is this useful? Let me tell you one thing, which is when you talk about the thermal ensemble, you close your eyes and say that, well, if you give me a Hamiltonian, if you give me the initial state, I know the energy density, therefore I know the effective temperature, therefore I know the Gibbs ensemble, right? Now, why is it the Gibbs ensemble? So you go back to your first course on thermodynamics or statistical mechanics, and you say, oh, well, the Gibbs ensemble, it must be the Gibbs ensemble because that's the ensemble that sort of maximizes entropy given the constraints in my system, right? That's what you learn in your first course in thermodynamics. Here, the idea is very simple, that if I have to now write down a universal form for the entire ensemble, again, there should be an entropy maximization, and that entropy is the entropy of the ensemble itself. It's not the thermodynamic entropy, it's the entropy of the entire ensemble. And what that means is, if you deep thermalize, then the projected ensemble tries to cover this Hilbert space as ergodically as possible. Now, that's the sort of takeaway. So for example, as a trivial example, or sort of the first non-trivial example, or the least non-trivial example, suppose you do not have any symmetries or conserved quantities in your dynamics, then you should get the maximally random ensemble, and that's just the Haar ensemble. If you have some symmetries or conservation laws, all you need to do is you need to deform this Haar ensemble by some effective density matrix, which would be your first moment. Okay, so that's the construction of how you construct these maximum entropy ensembles. So it's a different question whether your ensemble does go to these universal ensembles or not. If it goes, we say that the system thermalizes deeply, not only thermalizes, but thermalizes deeply. If it doesn't, it doesn't. Okay, so why are we actually interested in this? So the reason is that deep thermalization or higher moments of this ensemble is actually a finer probe of ergodicity and thermalization compared to conventional thermalization, and this will probably answer Arti's question, which is, suppose I want to sell you a device which is supposed to scramble quantum information, okay? But instead of, and unitarily, okay? However, I actually have a very, very rubbish device which has a lot of decoherence, or maybe, the initial state that I prepared is also sort of extremely decoherent. And once I give you that, I will, very easily show you that, well, the reduced density matrix at some late time is exactly equal to or proportional to the identity, normalized identity. And in this way, I can convince you that, I have given you a very, very nicely scrambling quantum system and sort of be done with it. However, the point is that if there is decoherence, which means that the device is bad, then the reduced density matrix goes to identity or some maximally mixed ensemble or maximum entropy ensemble, maximum entropy density matrix, simply because that my device was buggy, not because my device was a good unitary scrambler, right? One way of seeing that is that the measurement or the state would be independent of the measurement outcomes, because the system just simply decohered, and before you had done any measurement, you got identity. However, or that's in other words, the k equal to 1 result is indistinguishable from conventional thermalization. However, if you knew about deep thermalization, you would say that no, let me not stop at k equal to 1, show me what happens for k equal to 2. Do measurements on the bath, compute the ensemble, and show that the second moment also goes to the Hall ensemble. And why is that important? Because the second moment are completely different. For example, you see the Hall ensemble has this extra piece, which is the swap operator over the two replicas of the Hilbert space for the second moment. That's not something that you will get if you had decoherence. Okay? So in this sense, deep thermalization indeed is a finer and sort of a higher probe of ergodicity and thermalization. Okay? Good. So now the point is, if I'm interested in these kinds of setups, then I need to define these ensembles for mixed states, because I might have measurement, I have decoherence and everything. So how do I actually, what are the sort of two stereotypical ways of getting projected ensembles from mixed states? And these are two sort of really equivalent statements. One is that your initial state itself is mixed. Your device, your circuit might be perfectly unitary, but your initial state is mixed. So this goes under the name of state preparation and measurement errors. So in this case, of course, because this is a mixed state and your circuit is completely unitary, you retain the same amount of mixedness at all times, which means that when I do measurements, the conditional states continue to be mixed. Okay? The other possibility is that everything is nice. Your initial state is pure, your dynamics is completely unitary, but eventually, when you sort of do these measurements on the bath, somehow your measurement device is slightly buggy, and you end up with losing some of the information. And that amounts to again tracing out a part of the system, and that again gives you ensemble of mixed states. Okay, so and morally speaking, these two sort of setups are equivalent, and in this talk I'll mostly use the second one, but under some transformation I could have also used the first one. Okay, good. So what are the given all this background on deep thermalization, projected ensembles, and so on, what are the questions that we are actually asking? So we are roughly going to ask, or broadly going to ask, two questions. What is sort of the universal statistical properties of these partially projected ensembles? We call them partially projected ensembles because you did not project the entire bath, but you sort of projected only a part of it, and the other part you sort of lost to decoherence. So what are the limiting forms of these ensembles? Are they deformations of known maximum entropy ensembles or not? That's the first question. The second question, and that's sort of really the meat of the talk, which is that what are the information phases of this partially projected ensemble? This is something that I alluded to at the very beginning of my talk, that how is the information shared between R, which is my reference subsystem, and S, which is the part on which measurements are being done. And then I'll talk about something called accessible information and so on, and try to sort of understand the information structure using these quantities like accessible information and some other quantum information theoretic concepts. All right, so we need to define deep thermalization for mixed states. So how do we do that? The conjecture here, or let me just give you the answer straight away, is that the projected ensemble of mixed states is the partial trace of the projected ensemble of pure states on an augmented system. Okay? And when I say an augmented system, I don't mean I'm physically augmenting the system. It's really a tool that I am using to define these mixed state projected ensembles. So what am I actually doing? What I'm saying is the following, that suppose I have a mixed state to start with, there is some circuit which acts on it, and then I have this similar setup. Now this whole thing I can sort of fold into an effective density matrix, very likely mixed, between R and S. Okay, at this stage this is just a mixed density matrix that I've gotten by tracing out E. Now this mixed density matrix I can write as a purification of I can write a purification of this mixed state as follows, or in this way. what that means is that I have put some extra degrees of freedom, let me call them x, and I have defined a pure state on this sort of augmented system, augmented, or the original system augmented with x. And what I have done is I have taken a trace over these augmented degrees of freedom, right? So the idea is that you choose the pure state in a way on this augmented system such that tracing over these auxiliary degrees of freedom gives you the original density matrix that you had in mind. And of course, the purification is not unique. You could have written many pure states whose partial traces give you the same mixed state. And it should not be in some sense, because at the end of the day, this is something that I introduced to sort of solve the problem. And let me just tell you before you get worried that our answers actually don't depend on the precise purification that you choose, and as it should be, because as I said, the purification is just a mathematical tool. Good. So now here is the flowchart of how the ideas work. All of this can be made completely rigorous, which was done in sort of these papers. So you have this pure state on an augmented system. Remember, this was x, this was r, this was s. You do the measurements on s. Once you do that, you essentially get a projected ensemble of pure states on R union X. And if you have no symmetries in the problem, in exactly the way I defined towards the beginning of the talk, you get a maximum entropy ensemble over here on R union X. And all you then need to do is, because partial traces factorize over replicas of Hilbert spaces, the kth moment of the partial projected ensemble is actually given by this partial trace over this reduced density of this kth moment of the projected ensemble. And then if your circuit was scrambling, then R union X would thermalize or deeply thermalize, which would mean that this would actually go in general to what I said, a Scrooge ensemble, which is a deformation of your Haar ensemble, given the purity of, given that this state actually has a fixed or a finite purity. It's not a maximally mixed state. So once you do that, all you have ended up with is the partial trace of a sort of generalized of a Scrooge ensemble. And this tells me that the universal ensemble describing these ensembles should be partial traces of pure state maximum entropy ensembles, which are then defined on augmented systems. Two sort of okay, this is the result. And one interesting sort of limiting case of this is if the rho of t that I had a flat non-zero part of the spectrum, namely all its eigenvalues were of this form, then what actually happens is, you can again show this completely rigorously, is that the partial projected ensemble is actually given by the partial trace of a Haar ensemble. And this goes under the name of generalized Hilbert-Schmidt ensembles and so on. I mean, that's just for making connections to known literature. Okay, right. So now this sort of tells you that what is the definition of these partially projected ensembles. But at this stage, you are well within your rights to ask the question that fine, this is all well and good, but when does this happen? Because there are too many moving parts in this at this stage, right? Because there is a system which is scrambling, maybe there is a very random state at the end of it, but then I am sort of making three partitions in the system. I'm calling one the reference, I'm calling one the environment, I'm calling one sort of the measurement part of the subsystem. So one should ask this question, that when do you actually see this, or to what accuracy do you actually see this? And one should be able to make this rigorous. So in order to do that, let's say that I have, let's sort of help ourselves. Let's make life simple and say that I really have a very random state at the end of the day. It's a sort of maximally scrambling circuit that I ran for a very long time, and I ended up with a Haar random state. Now my reference subsystem occupies fraction gamma of the total system. The measured part occupies fraction p, and the part that I traced out occupies fraction 1 minus gamma minus p. Now, of course, you can see this, that if you trace out, for example, a lot of the degrees of freedom, suppose E is very large, then it intuitively makes sense that you have actually lost a lot of quantum information, you have lost a lot of quantum correlations. So then the projected ensemble is not going to reflect a universal form. On the other hand, if E is nothing, you have not traced out anything, then they should again go back to some pure state Haar ensemble like behavior. So there must be some condition on these fractions which would ensure that the deep thermalization in the way I mentioned does happen. And that's basically the statement of this theorem, which says that the kth moment of the ensemble satisfies the maximum entropy moment by or is less than epsilon with a probability at least 1 minus delta if some conditions are satisfied. Okay. Now, forget about all these details. Note that in this inequality there is ds times dE on the left, and it must be greater than some function of dr. So this tells you that for deep thermalization to happen, dr must be less. Dr is the Hilbert space dimension of R, ds and dE are the Hilbert space dimensions of S and E. Dr must be sort of less than some function of ds times dE, which means that your subsystem that you are interested in should be sufficiently small such that you get deep thermalization up to the kth moment with some accuracy epsilon. Okay, that's really the sort of that's really the content of this theorem. You can sort of make it a bit more physical by saying that if you really want epsilon to decay exponentially with the system size, because you want epsilon to go to 0 in the thermodynamic limit, you sort of require a certain condition. Okay. So this is important because we will use the fact that my partial projected ensemble is a mixed state deep thermal ensemble in the latter part of the talk. Good. So as I said, you need smaller r for it to be a better approximation. That's really the gist of this slide. Good. So we have some answers that the partial projected ensembles sort of asymptotically are described by sort of partial traces of maximum entropy Scrooge ensembles. Let's now move to the last part, and I'll use this result in this part of the talk. But to introduce this part of the talk, let me just give a small background, which is, given that I have this setup where I have a very random state with 3 parts, one can ask the question that, well, why are you doing all this song and dance? Why don't you just trace out E and then you are left with a mixed state on R and S? Why don't you just compute one of the innumerable entanglement measures known for mixed states between R and S? And of course you can do that. So people have done that, and you can compute, for example, the negativity. And if you compute the negativity, so this is P, this is gamma, what you see is that for R random states something like this emerges. Okay. So in this part of, if gamma and P both are very small, then you basically have no entanglement between R and S. That again physically makes sense because if gamma and P are both very small, then you have traced out a large part of your subsystems. You are not left with enough degrees of freedom to mediate the quantum correlations and so on. But these 3 colored triangles have finite negativity, in fact have volume law negativity between R and S. I'm not going to go into the details of why are these 3 triangles differently colored, but just take my word for it that these 3 triangles have finite negativity between R and S. Okay, and we'll keep this in mind because what I'm trying to point out here is that negativity is not the full story. There is more to how information is shared between R and S than what's apparent from negativity. Good. So again, let's go back to our partial projected ensemble. So what I have done is I've traced over E, I have measured S, and I've gotten this ensemble. Now, given that I have this ensemble, I can construct something called a classical quantum state. What that means is I take the conditional state given the measurement outcome S, take a tensor product with the classical state ZS, and then sum up over all of this. Now, given, because this is the ensemble to which I have access to, because I've measured the subsystem S, I don't actually have a quantum state on that subsystem, right? And of course, once I've constructed this classical quantum state, I can compute the mutual information, for example, between R and S. You can compute the negativity, it doesn't really matter, but I'm computing the mutual information because it has a certain meaning here. So this is sort of what the mutual information is given by. So this is really just the von Neumann entropy of the reduced density matrix of R minus the reduced or the von Neumann entropy of each of the conditional states in the ensemble weighted with the probability. Okay. Now, interestingly, this is connected to a very, very central quantity in quantum information theory, and that's called the accessible information. So I'll take sort of 30 seconds and slightly change gears and try to motivate this from a quantum information-y perspective. So think of a quantum information task where you have to send some classical information over a quantum channel. This is just a jargony way of saying that there is some classical information, could be classical bit strings, and Alice wants to send it to Bob, but she doesn't want to send the classical bit strings. She encodes each of her bit strings in a quantum mechanical state, and then sends the quantum mechanical state to Bob. And what Bob can now do is Bob can take that state and do whatever positive operator valued measurements he can to sort of get as much information as possible about what exactly did Alice send. So originally Alice had some classical probability distribution. Bob also gets a classical probability distribution given that he does measurements. And what quantifies whether whether Bob can actually learn something about Alice's information? That's basically the mutual information between the two sets of classical variables that you have, right? That's what tells you whether two distributions are correlated or not. But of course, and that's really this. But of course, Bob has full freedom to choose what measurements he wants to make. And he wants to choose a measurement so that he maximizes the information that he can get. So that's actually the definition of accessible information. That's sort of the maximum over all measurement basis or measurement choices that Bob can make of the mutual information. Now, unfortunately, this is called accessible information. Unfortunately, computing this is an NP-hard problem. So you cannot compute this. But what you can compute is something called a Hall05 information. This is named after Alexander Hall05, who sort of derived this seminal result, which is that the Hall05 information is an upper bound to the accessible information. Okay, and that's important. See, the Hall05 information being finite is useless because it's an upper bound. However, if the Hall05 information is 0 or it goes down exponentially with the system size, that's cool because then you can say that if the Hall05 information goes to 0, then your accessible information also goes to 0, and that just means that you cannot access any information. Okay, and notice that this Hall05 information is nothing but the mutual information of the classical quantum state that I had actually written down. You see? Good. So that tells me that if there has to be some accessible information shared between R and S, then the Hall05 information must be finite. Okay. So since in the interest of time, I'm not going to go through how we calculate this. Let me just go to the result, which is, remember this is my entanglement phase diagram. You see this red line, it cuts through this phase diagram. In the blue part, the Hall05 information is finite. Okay, that doesn't say much, as I said. However, in this green part, there is 0 Hall05 information, which means that even though there is entanglement between R and S manifested in negativity, there is no accessible information. So this is like a finer characterization of how information is encoded between R and S in this setting. So this is like a new, these are new information phases. There is no analog in bipartite systems, I must add. This is a strictly tripartite setup. And okay, there are some numerical data that all of this theory does work out if you do calculations and so on. I'm going to into that. So let me just stop with the summary, which is that I sort of gave you a definition of dethermalization for mixed states, and then I talked about how that helps you define information phases. Okay, yeah, thank you.
Thank you. Now the session is open for questions. Please,
Yeah, thank you for the talk. I have two questions actually. First, about physically looking at a measurement invisible quantum correlated phase. Does it mean that the projected ensemble that I have is not like reflecting the main thermalization properties of the circuit? Like you can comment.
No, that's not true. So as I said, both all of this works out when deep thermalization does happen. So these are both deep thermal ensembles. Okay, but the nature of the deep thermal ensembles are different. Okay, because the mixed state deep thermal ensemble also depends on how much you trace out and how much you measure.
Exactly, yeah. So one another question, like the result you presented upon the sizes of the S of the different Hilbert space segments, that was calculated based on the hard random state.
Correct. Yeah.
But when we are generically doing this, it is based on like a generic initial state which is not hard random.
Sure.
So how does the result?
So that's the bit that I skipped over. So basically the point is, if you have like a generic situation, then at some time scale, you will eventually see this. So that's what these results are saying. See, this is time, and eventually, for example, in the measurement invisible phase, you see that this goes down exponentially.
Okay.
Yeah. So so if your circuit is scrambling enough, you will see this at late times. Okay.
So this is about the decoherence or noise that you mentioned. Are those acting on individual parts of the system, like CPTB maps let's say amplitude damping on one qubit.
It could be a CPTP map, but it doesn't have to act on the individual parts. It can also act collectively on.
But if I take it over the whole system, like amplitude damping tensor all the qubits, then what happens?
In the initial state?
No, to the entire idea that you can tell thermalization apart from decoherence.
Well, okay. So if you do amplitude damping, then of course it's not decoherence anymore, right? It's you are sort of jumping on. I mean, you're putting a jump operator which takes you to the all down state, right? So in that case, it won't. In that case, you are sort of pushing it to say the all down state. For example, suppose you put a sigma minus as your jump operator, then you're trying to push it to the all down state, and that would be your steady state if you did not do anything. Right? Now, then what happens is it becomes a question of time scales, that at some stage you also have to do measurements, and averaging over measurements is like dephasing. So then it becomes a competition between the dephasing of the measurements and the jump operators of sigma minus. So and then there's an issue of time scales there. But the point is, if you have a situation like that, because at some stage, let's say that the spins were generally pointing down, but you did a measurement on a large part of the system, then essentially what has happened is that your initial your circuit itself is not scrambling enough, so you won't get a deep thermal ensemble to start with.
Can I refine that question? So let's say that the center of the block sphere is preserved by the mapping. Amplitude damping was a bad example. Let's say the center of the block sphere.
But that would mean that it's dephasing. But if it's dephasing, then everything that I said will go through.
Even if it's over all the qubits.
Even if it's over all the qubits, yeah. Okay. Because I did not make any assumptions over how you put the decoherence. Right?
Thanks. Very nice talk. You showed us kth moments of these. So if you define the generating function of these kth moments, there's an exponential involved. And is there some meaning to be ascribed by the Legendre transform of that function that keeps the information content constant? The Legendre transformation of that
maybe, but
multiplier would play a role of what temperature you should.
No, I mean I think that's probably pushing the analogies too far. That's it.
But has the Legendre transformation been discussed?
Not really, because the kth moments themselves are quite hard to compute. So because the only analytic way in which you can compute these are considering Haar random states, where you do Haar averaging and so on. That involves permutations over k replicas. That's tractable only up to some k.
So is there anything operationally different if the system in question actually thermalizes to a generalized Gibbs ensemble as opposed to a Gibbs ensemble?
Yes.
In terms of deep thermalization?
Yes. So then the deep thermal ensemble is actually given by the maximum entropy ensemble, whose first moment gives you the generalized Gibbs density matrix. For example, you could have asked it in a very simple setting of free fermions, but suppose you put enough ergodicity as free fermions allow you to do this, then what you see is that the ensemble covers the space of all Gaussian states with maximum coverage.
Okay. Now let's
Thank you.
Thank again Professor Rai. Thank you.